My name is Arjun, and for my winter project, I continued my internship from my EXP in the summer, which was about data science and analytics for esports. So I'm just gonna outline what I did this term. So the first thing I did this term was I updated a cast function that I created as part of an analytics package I made for the game. So essentially, I had previously made this cast function in the summer during my actual EXP part of the program, but because my code is public, we have users actively using it, and there was an error with the function. So then based off of the feedback that we got, I updated the function and it was properly able to return this this statistic called cast percentage. And what cast percentage essentially is, it's the number of kills, assists, survivals, and trades a player gets out of the total rounds. So for example, there's 5 rounds and you got a total of 2 of either of these 4 values, your cast percentage would be 40. So then that's what you can see in that table over there for a sample match. You have the 10 players, there are 10 cast percentages, and 0.67 is a 67% cast percentage, not 0.67. Then you have the number of kills, assists, survivals, and trades. So this is the first part that I did this term. And the second function I made, which is completely brand new, was a rating function. So in CSGO competitive games, players are given a rating based on how they perform. So our library lacked this feature and it was requested by some users. So the big company for esports and specifically CSGO analytics is called HLTV. And what HLTV creates is a rating statistic, which is made by a summation of kills, assists, survivals, trades, and other impactful things a player can do in a match. So HLTV had 2 ratings, ratings 1.0 and rating 2.0. So rating 1.0 was publicly available in the calculation, but rating 2.0 wasn't. And we wanted to implement rating 2.0 in our library. So we found a user in our library who actually found a reverse engineered calculation of rating 2.0. And using that reverse engineering calculation, I made a function to calculate the player rating for a match and also player impact. The player impact is a subset of the player rating, and it's also useful because it's more focused on kills and the amount of damage a player does. So you can see over there, that's the 10 players, that's each of their 10 impacts, and that's each of their 10 ratings. The rating goes between generally 0 to 3, but most people fall between 1 and 2. Then the bigger part of what I worked on this term was a win probability model. So rather than purely focus on analytics with those functions that I was previously talking about, one of the larger goals of this project is to create a win probability model that uses those functions and player actions to predict the outcome of a match and how impactful a player is. So our win probability is based on game states, which are at a specific time in each game. You have information such as player health, player armor, and team equipment value, and that would essentially influence how likely the teams to win. For example, if team A had 5 players alive and all of them had armor, and if team B only had 4 players alive and none of them had armor, team A would be more likely to win. And then you can also quantify player actions and how impactful they are. So if you look at that graph, it's an example of a win probability model for a whole match. So over here you have when the counter-terrorist team, one player kills a team member of the terrorist team, their win probability increases by 20%. So you can also quantify not only win probability by on a macro level as a team, but you can quantify how much one player contributes to win probability, and that's another statistic called win probability added. So that's part of this. So the first part that I mainly did this term was create functions to generate these game states. So I had to create 4 functions. So as I mentioned previously, in a game state you have information such as player health, player armor, etc. So what generate team vector state does that it takes in a frame from the whole match and returns all the information, including player health, how many grenades they have, how much ammo they have, and stuff like that. I'll show that on the next slide. What generate world vector state does, it returns basically information about whether a bomb has been planted or not, because in the game, one of the objectives for the terrorist side is to plant a bomb and essentially let it explode to win the whole match. And obviously, if the bomb is planted or not, that depends how probable the terrorist team is to win. So that's the second aspect of it. Then generated vector state returns a combination of generated team state and generated world state, and generated game state essentially runs the generated vector state function, but instead of like just doing it on a frame by frame basis, you can pass it a whole round or an entire game, and almost like loops through like all the frames in each round, all the frames in the whole match. And instead of returning like a JSON output, it returns like a Pandas data frame. So I'll show you the example. So this is the output of generate vector state. So as I said, generate vector state returns the game state information for each side and the world state information. So like for example, full HP players remaining, HP players remaining, like these are like how many players each team has. So obviously that would have an impact on the match. And you have HP, which is health, armor, which is the amount of armor, helmets, which is like another type of armor, but for the player's heads in the game. And then the other four values are all like equipment types. So like flashbangs, incendiary grenades, molotovs, smoke grenades, they're all like different types of grenades in the game. And one thing you could do for this is like you correlate like the number of like grenades you have to like the win probability. So for example, if you find a pattern after running the model that having more flashbangs or like using more flashbangs increases win probability, you could essentially correlate like having more flashbangs is like more impactful than having smoke grenades for like example. And then the world vector state, which is like global at the bottom, you can pass it a map name. I just put yes there as an example, but it can be any map name. And then bomb planet tells you like if the bomb is planted or not. Seconds remaining is like how much time is left in the match. So like I just said, there's like multiple frames in the match, and like each one happens at like specific time. So that tells you that, and like that can also be used for win probability, because if the bomb is planted and there's not much time left, the terrorist team has a higher probability of winning. And then bomb side, this field is empty because there's no bomb planted, so there's no applicable bomb site. So this is essentially the output of generate game state and or generate vector state, and then generate game state returns that output in a data frame and has like one row containing all this information, and like depending on how many frames you have. So for example, if you have a round, you'll have like X number of frames, and if you have a game, you'll have like the number of frames in a round multiplied by how many rounds are in the game. So like you can get up to like 2,000 of these game states. And I didn't get to completely finish the model yet because I had to do all this setup, and I was also maintaining the library at the same time because it's a unique experience, like having the code like public and like having to interact with people using it. So I basically had the setup ready, and the next time I'm gonna like create the actual model. And then the fourth thing that I did was publish my code to like the Python package index. So my library, as I mentioned, was on GitHub, and we have over like 2,000 to 3,000 users right now. And ultimately, because it's like production level ready, we were able to publish it on the Python package index. And you can now, rather than like including the library, you can call like the function pip install, which is like widely used for like bigger packages. So I worked on documentation for that, and it's been live there since the beginning of February. And yeah, you can see that we have a Discord. That's where like I interact with people using it. And I also submitted my research to the IE ISEC conference, which I'm yet to hear back from. But yeah, and then future work, as I said before, I want to actually develop this win probability model and get it added to the library, because I think that'll be a core feature once it's added. And then ultimately, there's like scope to like write and publish a paper related to like these analytics, because it's like such a fast growing field and there's like a growing need for it. Like with just our library alone, we've got so many users. So I'm looking forward to like completing that in the spring, and thank you.
Great.